Okay, so in part one and two of engineering project finance, we talked about the concept of why it's important for engineers to engage with the finances of the project. And then we looked at the concept of discounted cash flow and how that investors are looking for a return on their investment, which is important to make sure that they will invest in your project. One of the key parts before you can actually perform a discounted cash flow analysis is to decide how far into the future your project is going to last. How long do you have to spend maintenance? How long will the revenues be considered? And this is the concept of project lifetime. Now, project lifetime may not match the same as from an engineering concept as it may from a financial concept. The project lifetime for a bridge, for a building, may be 25 years from a financial standpoint, which is a typical mortgage, whereas from an engineering standpoint, the same building may last for 50 or 100 years. So it's important to establish what is your lifetime of your project. And the assumption here is that construction time for an asset will typically be a small fraction of the total project lifetime. That statement does not generally apply to electronic products. If you consider the concept of a mobile phone, an Apple iPhone, then the actual development time for the phone may actually exceed the lifetime of the phone, because a typical lifetime of a new phone is now about 18 months to 2 years, whereas the development time might take 2 to 3 years. So it depends what industry you're in. But if you're in the industry of building power stations, then the power station may be built over 3-5 years, and the lifetime of the project may last 20, 40, 50 years. The key thing here is that loan payments to invest in the building of the project will probably cease much sooner before the revenues will cease for a project. And conceptually, you need to deal with the lifetime of the project from a financial standpoint and also from an engineering lifetime project. Engineering judgment comes into this. And this is where the engineer and the financial director will meet and have a long discussion about how they should define a project lifetime. The financial person may define project lifetime as perhaps 25 years, which is when they want repayment of all the loans, whereas the real life of the project is actually more like 50 years, and the revenues beyond 25 years are effectively pure profit into the system. So let's look at our early example, and we can define a very simple formula to calculate out the present value of a single cost incurred some point in the future. If we have a discount rate of 5%, then the cost of £100 in 1 year's time, as we have seen it, is about £105. In other words, £100 cost today is equivalent to spending about £105 in 1 year's time. In 2 years' time, it's compound interest, so we can generalize this out to n years. £100 of 1 plus 5% raised to the power n will give you the cost of that £100 in 5 years' time. But similarly, you can turn the costs around by working out what the future costs are back in today's money, and the equation's given there. The last example was just one cost for 1 year, but actually your net present costs are the summation of all the costs in all the future years across the lifetime of the project. And these could be costs of things you're spending on the project, and equally it could become income from the project. So you may spend £100 or £105 in 1 year, but you may benefit £120, and you need to relate that back to how you relate that to the cost and present value. And here's a simple equation to calculate it out. So we've looked at the costs and worked them back to net present value, but we can also look at benefits or the income. And to get the net present value of a project, we subtract the net present benefits or costs from the benefits. So the example I said, in 1 year's time, if it costs £105, but you get a benefit of £110, then the net benefit in 1 year's time is £10, and you relate that back today by dividing by 1.05 to get you the net present benefit at today. And you do it 2 years, 3 years, 5 years, 10 years, right across the life of the project. The cost-benefit ratio, or the benefit-cost ratio, the higher value that is, the better. Whereas if the benefit-to-cost ratio is less than 1, the project is non-economic. Now, we look at HS2, the building of the high-speed train link. There's a lot of justification of why it's good, but there's been very little analysis and printed analysis of what the true benefit of laying HS2 will be. Now, sure, if HS2 came up as far as the northern cities or into Scotland, there would be considerable benefit because then you could save the time. But is a saving of 10 minutes on a journey time between Birmingham and London really beneficial? There's another way of measuring the return from projects, and it's the concept of internal rate of return. What they do for an internal rate of return is they set the net present value to 0, and they work out the interest rate that would need to apply to generate that. I would not recommend you use internal rate of return because it has great difficulty in dealing with different payment schedules over the life of the project. And it can actually be used to make a project look less or more attractive by adjusting the period of time that you take the project over. It masks a lot of the detail, whereas net present value is a much more pure way of considering the problem, but does require that you make an estimate of the interest rates over the foreseeable future. And if we take the situation today, it's very difficult to estimate what our interest rates are going to be over the next 10 years. However, and can safely predict they will not be 0.1% like they have been for the last 5 to 10 years. So far, we've talked about the financial benefit of projects, but there are also incommensurable values. For instance, the environmental value. We're all aware of global warming. We're generally aware that this is not good, but how do we relate to the cost of global warming? And this is fundamentally the argument that Donald Trump uses. How do you quantify the cost of global warming for the next 5 years against the cost of the next 50 years? Now, sure, if New York City was flooded in the next 5 years, I'm sure Donald Trump, who is into property, would be very, very concerned about the cost of it. But because it's more difficult to quantify, that's why economists and ecologists look at things like carbon footprint. I'm aware that me flying back and forth to China has got a huge carbon footprint, but the justification is if I fly there, it's a lot cheaper for me to fly there from a carbon footprint standpoint than it is for all these Chinese students to fly to Glasgow. So the justification is it's actually carbon beneficial for us to fly out there rather than them to all fly here. It's very difficult to try and attach monetary equivalent value on environmental issues. It is often easier to deal with financial analysis and perform an environmental analysis separately because any monetary equivalence can also always be challenged by those not supporting the arguments. An example of this is the EU some years ago introduced the concept of carbon footprint, and they charged companies a tax on how much carbon they produced. Well, all that happened was that those companies that could reduce their carbon did so, and then took these carbon credits and sold them on the open market to companies such as power stations who could not reduce their carbon footprint. And they actually didn't benefit the overall market. It just meant they created a trading commodity in the concept of these carbon certificates that was never intended. And in fact, most of the companies which reduced their carbon, all they did was they offshored the manufacture of their products to China, India, Vietnam, and places like that, where the carbon certificate had no value and no problem. Next thing I want to talk to you about is sensitivity analysis. And for any project, you should look at what would happen if your predictions were not correct. This could be applied to a power station where if you predict a certain usage of electricity and it actually runs at perhaps only 50% capability, then how much more expensive is the electricity? Equally, if you're producing mobile phones or a product such as that, if you only sold half of what you could sell that you would normally sell, then you'll discover that it's very expensive for your business. Over the last 3 months, there was a report that this is the worst sales of cars in the UK for the last 15 years. It has a huge impact on the automotive industry because no one has been shopping for cars over the last 3 months. It's important you understand how sensitive your project is to either increases or decreases in demand. The example that's shown here is the example of power generation, and the interesting concept here is, how effective can you operate, say, a nuclear power plant at 50% capacity? There are some products and some projects that they have to operate at 100%. There's also compare the alternatives. Whereas your project designed for 100% operation may be the most effective, but if it only operated at 50%, it might be less effective. And you should compare your project proposals with other similar project proposals, or indeed doing no project at all. How does it compare with doing nothing? And it's important to establish this so that if you're challenged by your sponsor or by the client, you can say, we've looked at that and this project is always profitable, or it's profitable under these circumstances, because the client may be able to do activities within the environment to encourage usage of your project, such as adding tax relief or providing discounts or benefits. We've looked quite a lot at some of the techniques within financial projections. We've looked at levelized cost, we've looked at discounted flash flow, and we've looked at net present values. We also briefly mentioned the internal rate of return, but I suggested that that is not a good measure because it depends and can be adjusted. All of these measures are great use of spreadsheets, and really it's the only way of sensibly being able to look at the sensitivity analysis of your project by running a spreadsheet under different circumstances. The mathematics behind them are very simple. The key engineering challenge is using and choosing the most sensible and realistic and defensible parameters for doing these analyses. You would never do the financial benefit analysis of a nuclear power plant over 5 years. Similarly, you would struggle to do the financial benefit analysis of, say, a laptop over 20 years. You need to choose realistic timescales for the project you're proposing. And finally, as engineers, you need to be central in these discussions about your projects. They are your projects. Don't leave it to others to make decisions on whether your project is successful. I'll just leave you with one final point. In building business plans for projects, which I've done many times over the years, you can make any project look successful or look like a failure by tweaking the revenues and the costs by about 10% in the opposite direction. I'll leave that with you, and now you think about what numbers you should apply to your projects. Thank you.